number. Okay? We talked about how the table is organized by increasing atomic number. Okay? However, today we're going to talk about how you can have the same element, but different types of that element, or different types of the atom. Okay? However, atoms that are of the same element. So, one sodium atom compared to another sodium atom, or one helium atom compared to another helium atom. Okay? You can have different types of atoms that are the same element that have different number of only electrons or neutrons. You cannot have a different number of protons, or you don't have the same element. Okay? I'll explain in just a minute. So, if the atom gains an electron or loses an electron, it gets a special name. It is still that atom, but you add the word ion at the end. Okay? So, this is a sodium atom. Sodium is atomic number 11. So, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. Okay? So, 11 protons, 11 electrons. That's a regular sodium atom. A sodium ion is, you have 11 protons still, right? But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So, here I have 11 protons, 11 electrons, and 11 neutrons. Does everybody see that? Okay. I mean, you can't see it, but those would be in the nucleus there. Okay. Here, I have 11 protons still, because it's still sodium. I have 11 electrons still, or neutrons, but my electrons are a different number. Let's say they're 10. Okay? If this number is different, if the number of electrons is different, you have an ion. Okay? And we represent that by having the symbol of the element and either a plus or a minus sign up the top of the right corner. Okay? This is positive because there are more positives than there are negatives. Okay? So the whole atom carries a positive charge. What if, instead of having 10 electrons, it had 12 electrons? It added an extra one. I still have an ion, but instead of it having a positive charge, it now has a what charge?
Negative.
Negative charge, because the negatives outweigh the positive. You see what I'm saying? Not sure if that makes sense. Okay, so if I have a different number of electrons, I call that a what, class?
Ion.
Ion. Good. Now, what if I have a different number of neutrons? Okay, in that case, we have what's called an isotope. Say isotope. Isotope. Okay, that's coming up next. So, isotope. A different number of neutrons. Okay, raise your hand, please. Don't just shout out. Okay, so let me show. Well, actually, let's write down this first, and then I'll explain it to you. So, write this down, and then we'll do some more explaining. If an atom has more neutrons than protons, that atom is an isotope of that element. Since neutrons are neutral, however, okay, because neutrons don't carry a charge, it does not give the atom a charge like an ion does. Okay? All that happens is the nucleus gets heavier, and therefore the atomic mass of the atom goes up. Does that make sense? We'll talk about atomic mass here in just a little bit too. Okay? So, everyone have this written down? I'm going to change it back to the white box. Okay. All right, let me explain this first, and I'll get to your questions. Okay? Okay, so let's say I have an atom with 4 protons, 4 neutrons, and 1, 2, 3, 4 electrons. Thank you. So, here's how many protons do I have?
4.
4. How many neutrons do I have?
4.
How many electrons do I have?
4.
Okay. Someone tell me, what is the symbol for this atom or this element? You can look at either my chart or the chart in your notes. What is the symbol for this element? Parker? Capital B, lowercase e. So, this is one atom of the element beryllium. Okay? That symbol stands for beryllium. Okay? This is the regular form of the atom. Let's say I add an extra electron. Not literally me adding one, but in the drawing, I draw an extra electron. Okay? Now, instead of having 4 electrons, I have how many?
5.
5. Okay? So what do I call this now? An ion. It is a beryllium ion with a what kind of charge? Negative. Good. Okay? A beryllium atom with a negative charge. Now, what if instead of gaining an electron, it loses an electron? Now it only has 3. What is it called now? An ion with a what charge? Positive charge. Good. Because the positives outweigh the negatives. Make sense? Okay. Now, let's say the positives and negatives are equal. But I changed the number of neutrons. 7. Now I have 7 neutrons. Okay. Now what is this called? A beryllium what, class? Isotope. Okay. Does it have a charge? No, because positive and negative are still the same. The only thing that changes is the atomic mass of this one atom gets heavier. Now, infinitesimally heavier. These small little guys have, you cannot even fathom how small they are, okay? And how little weight they have. But just by changing the atomic mass of the atom, it can cause the atom to behave differently. Okay? Now, we are only going to focus on elements numbers 1 through 20 in 5th grade. Okay? Because once you get past that, the rules change a little bit. Okay? For elements 1 through 20, all of these you can expect to be the same. A normal atom of that element will have 4, 4, and 4, or 7, 7, and 7, or 12, 12, and 12. Okay? We are only going to practice with those first 20. Because past that, sometimes the elements exist naturally with different numbers of these different parts. Okay? For example, oganesson, number 118. Oganesson has 118 protons, 118 electrons, but it naturally exists as an isotope with something like 177 neutrons. Number 118. Okay? So, the rules do change a little bit as you get further up into the chart. And really, unless you're a professional chemist, you don't really have to understand those parts. Okay? So we're going to focus on the pattern for 1 through 20. Make sense? Okay. Parker, question.
So on a magnet, would one side or would each side be ion and atoms?
I don't actually know, but you're on the right track. Trinity? That is a great question. I have asked that question to myself, I think, every year, and I can't remember the answer, to be honest. I would assume it can. A beryllium isotope with a negative charge, maybe? I don't know. It's a great question. I should look it up again. Landon? You realize what? Yes, I did. But I did on this board for the recording. Reagan?
Didn't they change the atomic symbol for oganesson?
Oganesson?
Yeah.
Yes.
Now it's OG.
Correct. They officially voted in 2016 to change that to OG. Or OS or something. No. ON? Something like that.
I think it's crazy though that we've had like over 118 and then there's still more. And then I feel like some of the names they've just been like so creative with naming it American, curium, einsteinium, and then you have like neptunium, plutonium, uranium. I just don't know why they had to name it all of that instead of trying to name it.
All right, one more. Connor?
What happens if you have like 118 protons? So 118 for. What if you took the mass is the same and the electrons is the same? What if you make the protons all the way down to 0?
Good question. What happens if I change the number of protons? Well, if I change the number of protons, I no longer have beryllium. Okay? What happens when you change the atomic number of an atom? Landon? Not lithium, that would be 3. I have 5.
Oh yeah, 5.
What's the symbol? It would become capital B, which is for boron. Okay? Now, would it be an ion, an isotope? What would it be? It would be an ion because the number of electrons is different than the number of protons. Okay? So it would be a beryllium ion with a positive charge, and if it's possible, I guess it would be an isotope too, because these are different. Make sense? Yes.
What if you put the protons to 0?
Then you would have nothing. You wouldn't have an atom at all. You would have just random particles flying around.
Especially because of the neutrons. If you didn't, are you saying if you didn't have?
All right, one more, Caleb.
Alright, so I have 2. Well, I don't check my what if atom has like 5, 6,
5, 6, 6. So the same thing, just the opposite way. 5 protons, 6 neutrons, and 6 electrons. It would still be a boron atom because it has 5 protons. Okay? Because there's more negatives than positives, it would be an ion with a negative charge. And that's what Trinity was asking. If it's possible, I guess it would be an isotope as well. I really don't know. I think you literally just call it isotope. Because it doesn't change anything about the atom, just makes it heavier. I really don't know. Okay? Alright, moving on. If an atom has more... Oh, we just wrote this part. Just kidding. Hold on.
Yeah.
Okay? Alright, atomic mass. The atomic mass of an element is the average mass of the different isotopes of that element. Okay? So, the decimal number up here is the bottom number. On my chart, it's the bottom number as well. But it's always the decimal number. Okay? Now, the unit for this mass, because you're going to have a unit, right? The unit for this measurement is atomic unit. AU. Okay? It's not grams, it's not centimeters, it's not milliliters. It is much, 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 much smaller than that. Okay? Atomic unit. Now, this makes sense. If you look at your chart, flip to your periodic table real quick. I'm teaching right now, wait. Okay? Notice number 3, look at the chart. You'll notice as you go up in atomic number, the atomic mass also goes up, which makes sense. If the nucleus has more protons and therefore has more neutrons, every time you add more, the mass should get bigger, right? Hydrogen has a 1.00794. You go up to helium, 4.00260. Go up to lithium, 6.941. Okay? Now, your decimals are rounded off a little differently than mine, but still, the fact still remains that it goes up every single time. Okay? That's the atomic mass. Now, This is also why helium will float, but oxygen and carbon dioxide will sink, right? If you get a balloon from the store filled with helium, it goes up, correct? But if you blow up the balloon, what happens? It sinks, okay? That's because helium has an atomic mass of about 4.003. Okay? That's one atom of helium. One molecule of carbon dioxide, okay? Carbon is about 12.011. Oxygen is about around 16. Okay, so this is 16 times 2. So you get 12 plus 32. One atom of carbon dioxide has about 44 atomic units. Okay, so helium is much, much lighter than carbon dioxide, which is why it will float, but carbon dioxide will sink. That's also why if you breathe in the helium from the balloon and you talk, your voice sounds all squeaky. Okay? The vibrations sound different in the lighter gas than they do in the heavier gas. Okay? Now, there is a gas, can't remember which one it is, but there is one that they've had someone breathe that gas in before and then they speak and it makes their voice much lower because it's actually way heavier than carbon dioxide. Do you know the name of it? No, it wouldn't be carbon monoxide.
I do know that amber is so heavy that actually you can pour it in and it can actually put it on.
Interesting.
So cool. It's called sodium hexafluoride.
Sulfur hexafluoride. There you go.
Yes, you can do what Nicholas said, but you can also fill a tank with sulfur hexafluoride and then blow up a balloon and just fill it with oxygen. And you can put it on top and it'll just float above it.
Mhm. Yeah.
It'll float on top of it.
Yeah. Some crazy stuff you can do with physics and chemistry. Atomic symbol. This should be a review from the vocab, which we discussed already. Scientists have developed symbols of 1 to 3 letters to represent each atom. Many of these symbols are derived from the first 2 letters of either the Latin or the English name. Now, in the first class, someone asked a very good question. Even in other countries, the symbols are still the same. Okay? The national head or whatever, or the worldwide head of science, establishes this is the symbol for this element. And the symbol is always taken from our language or Latin. Okay? But around the whole world, the symbol is still the same. Yes. Because again, remember when my chart was created, they hadn't been able to observe the newer elements for long enough to know really how they acted. That's because your chart is newer than mine.
No, it's like why did it?
Oh.
Why is it intended to?
Because okay, so it has to do with the fact that those elements they're radioactive. Okay. So what happens is they decompose or they break down so fast that we have not been able to keep them alive long enough to observe those things for sure. We can make a guess as to what we think they are, but they can't say it's a proven fact yet. Does that make sense? Okay. All right, moving on. Periodic table. The vertical columns on the periodic table are called groups. The horizontal rows are called periods. Keep in mind, in your notes, it says horizontal columns. This word here in yellow, you need to correct that in your notes. Anna, wake up. Horizontal columns are not a thing. It doesn't exist. Okay? So, change the word columns after horizontal to rows. Horizontal rows are called periods. Okay? So, this right here is period 4. Okay, that black outline is around period 4. This, the red outline, is around group number what? 2. Good. All right, count with me. Let's count all the periods. This is period 1, 2, 3, 4, 5, 6, 7. That's it. only 7. Remember, these guys get plugged into their appropriate periods up here. So this is technically part of period 7, and this is part of period 6. Okay? Now, what was I going to say? Don't remember. Sure, let's count the groups. Here we go. 1,
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
Nice. How many groups total, class?
18.
Nice. Okay? Now, each one has different relationships. Okay? All of the elements in group 1 are highly reactive. All the elements in group 2 are also reactive, but not quite as reactive as group 1. All the elements in group 18, they're highly unreactive. They don't react at all. Okay? So, you can identify an element just like with a graph, like a grid in math. You can identify an element by its period number and group number. Okay? For example, if I wanted to identify mercury, I could say it in, here's mercury. I could say it in period 6 and group 12. Okay? I could identify hydrogen by period 1, group 1. Okay? What about period 3, group 10? Well, that's HL or whatever this is.
NL.
Okay? NL. Period 3, group 16. Well, that's sulfur. Okay? So, that's one way you can kind of group up the periodic table. Not yet. All right, the last part we're going to do today, and then we'll finish the rest on Monday. There are 2 main groups. I think it's actually in the bottom of that same page we were just on. There are 2 main groups on the table, metals and nonmetals. Now, there is a small group of elements that are kind of in the middle. They're not really metals, they're not really nonmetals. They're called metalloids. Okay? Those are the yellow elements right here. Okay? They kind of make a stair stepper, which in your chart you have a stair stepper as well. Okay? That separates the metals, which is the vast majority of the table, and the nonmetals. Then you have the kind of the middle grounders, the metalloids. Yes. Some of the other things. Oh, so you mean your stairs are on a different spot?
No, I mean on that diagram, the black hole stairs is on the right side of DE and SE.
And that's how it is in your notes as well. Oh, I see what you're saying. Yes, the ones are kind of around the stair stepper. Some chemists debate over whether, so for example, some chemists might include Ga in the metalloids group. Some might include Al in the metalloids group. It kind of depends. But anything around this stair stepper could be considered either metalloids or even poor metals. Metals are really bad at it. Okay, Parker?
So most of the elements are metals.
Most. Hannah, go ahead. Connor, last one.
I do think. Why next to like UUQ